Sorry, I'm just trying to get the presentation on this computer.
It's not there?
It's not, it's all like letting me present. It just says, but I can plug my computer in. Is that okay? Is that like a problem?
There should be.
And the internet's not working.
Oh, is it? It's going on. Probably Google Docs. Oh, they didn't download it.
Are you guys all signed up on the?
Yeah, I signed it.
Awesome, thank you. I'll put these here in case you're forced to use
I
them.
usually plug mine in. It's already ready.
I put 2 extra video release forms out. Are you facilitating right now as well? Who's doing this session? Who is?
Alright, well, use Keynote next time. Great. Hi, I'm Varun, Ganapathi, head of AI at Udacity. I want to talk about how we estimate which students are going to graduate using very little data. And this lets us decide who we're going to focus on and who we're going to help, and also lets us improve our course content in a variety of ways. So the motivation behind this technology is essentially we want students, obviously, to successfully complete online courses. Everyone knows with a lot of MOOCs, people sign up and they enroll, but a lot of them drop out and don't actually finish. And we want people to finish. So what we think and what we have demonstrated is that analytics can help us understand student behavior prior to attrition and focus our interventions on students most in need. So we can understand what successful behavior looks like. We can also figure out really quickly if you're not going to succeed, we can have someone go talk to you and actually help you and help you evaluate what's going on. So that's kind of the motivation. So the input data to our problem is essentially events on our website. So students interact with our website in a variety of ways. They sign up, they go watch videos in sequence, they can skip around, they can take quizzes. Sometimes they pass a quiz, sometimes they fail, they submit projects. There's a variety of interactions that occur on the website. And so this is sort of our trace of the student's behavior. And when they succeed, it's like they've completed all the projects and they graduate. So that's like the last event, that's our goal event. And so on the right side, what I have is a diagram that's essentially kind of showing you what these events look like. So the first student, the first column is essentially student, they seem to be interacting a lot with the website, and each of these different colors is a different sort of interaction. On the right is a different student with fewer interactions at the beginning. And at the bottom, you can see, like, if we look really far ahead, we can see at the end, 3 months later, who graduated and who didn't. So essentially, we have labeled data. Without having to label it ourselves, we just have labeled data from the world, essentially because we can see the future after it happened. And here I'm just explaining specifically what occurred. The second student, for instance, watched only 4 lectures very sparsely, and then he failed the first project 3 times in a row. Our goal is to predict what will happen. And in this case, it seems fairly straightforward what will happen, but it's not always so obvious. So the first question is how do you formulate this as a machine learning problem? So student traces are a series of discrete events, and our goal is to predict a future event, aka graduation. You can even predict other outcomes, by the way. You can predict will a student pass or fail a project, when will they submit a project, things like that. And the model is essentially the same regardless. So the first problem is we want to be able to apply this model at any point in the student's trajectory. So, and the number of events amount of time the student has spent on the website is different for every student, obviously. Every day, a student's distance from the starting point has increased. So what we do is a very simple solution. We just train a different model for every prefixed duration. What I mean by that is we train a model for a student for whom we have 1 week of data, a student we have 2 weeks of data, and so on. And so for any given student, we know which model to apply. And the other cool thing is, whenever we have at the end, if someone graduates or fails, we have data for all of these models, right? Because we can always just look at the first week of data for a student, first 2 weeks, and so on. And so our goal, for instance, could be we want to train a model to predict who will graduate given 3 weeks of data. The class has started, we observe them for 3 weeks, what will happen? That's our goal. And we can do that for any number of weeks and so on. The week is a natural granularity, I think. We tried a couple of other ones. The week is really good because people have different sort of schedules per week, and this lets you kind of ignore that, and that's helpful. That's like a natural periodicity. The first model, this is our baseline model, is logistic regression. Essentially what we do is we one-hot encode the events of the students that occurred for that number of weeks. This is really simple. Essentially it says, after 2 weeks, what parts did the student complete? How many times did they fail a particular quiz? How many times did they pass it? And so on. And so you might expect something very simple. The intuition here is, for a certain number of weeks of data, we would expect successful students will have completed a certain amount of the course by now. But we're actually learning this from data rather than stating this ourselves. We also can learn things like, if you submit a quiz twice and you fail the first time, succeed the second time, that actually could be a positive signal because, you actually persisted rather than giving up after that. And so the model learns that sort of thing. So this is a very simple model. It actually still works pretty well. I'll show results for both of them. The second model is a neural network. Essentially, it's a bidirectional LSTM followed by a global max pooling layer, followed by fully connected layer and softmax. The paper gives you much more detail about how this works, but the input is essentially the same. The slight difference is the way you encode the notion of when a student completed an event. So the first model doesn't sort of care when you completed an event during a certain time period. Like if you did a particular thing anytime during the first 3 weeks, it counts the same. Whereas the second model, this model actually can know things like the velocity with which you do your work. So it will know, your velocity is really high, you're doing something every single day. Maybe it learns that, it can tell the difference between someone who's consistent, meaning working every day regularly, versus someone who just does everything in one day, right before the end. And that actually is part of the reason why it's able to perform better. In addition to, of course, like the representational capability of this is much more sophisticated than a logistic regression model. So to train the deep network, the objective is, as usual, negative log likelihood. Our goal is to sort of predict, maximize the probability of predicting someone will graduate. These are some details about model optimization. Hawk actually is the one who did a lot of the work, so he can answer any specific questions. Plus, he told me to tell you to just look at the paper, so you can do that as well. So performance. This is on 2 different Udacity nano degrees. We picked ones with much fewer students and much higher number of students, and also ones where the number of graduates, the baseline percentage of graduates is very different. This is to illustrate the fact that the model works well even if it's, the baseline performance is like 12%, like only 12% of people are graduating, and the other one, 41% are graduating. But the model kind of works in both of these cases. So it's not just predicting, no one's gonna graduate. That's like not what it's doing. So what you can see here is, first of all, I think the 2 things to keep in mind is the baseline model actually works pretty well. So you can see that like after 3 weeks of data, you already have like an 80% AUC for predicting who's going to graduate. And in this other nanodegree, you have a 90% chance, and that's because this nanodegree, the prior is already more accurate. But that's pretty good, and that's also very interesting because it means that it's hard to determine causality here, but it certainly is the case that the first 3 weeks, like how you start, already greatly affects like what's going to happen in the future. And so maybe this might imply that you should help people with their student habits really early in the process, or maybe this is a selection, like this is sort of a self-selection mechanism going on. It's hard to say, but the fact is it's very predictable very early in the process, which is really interesting. And the deep learning model, of course, does a lot better than the baseline model, as you can see here. And you can see that the improvement of the deep learning model is higher earlier in the course. Like for instance, in the first week already, there's a significant difference between the deep learning model and the logistic regression model. The next question is, how do you generalize this to new courses? So for this model, we required a lot of data per nanodegree. So we had, about like 6 months of data per nanodegree. We could train it on that 6 months of data and then test it on future data. But sometimes you'll have a completely new course, or maybe you'll have a course where the number of students isn't very high. And so in those cases, you won't have a lot of data. And so we've also done work, which I'm not presenting right now, but essentially where you can generalize from one course to any other course. And there are 2 different approaches to this. The first approach is essentially, the one you expect, which is you encode the features in some way that's sort of course agnostic. The model I showed you here essentially like the event of watching a specific lecture was encoded as a feature, and so it kind of learned that. But what you would want to do in the other case is encode the features kind of like, this is the third lesson after project 1, or this lesson, you should be approximately, like the instructors label the lessons with how long they think it will take, and so you sort of encode it that way. So essentially you try to come up with a representation that isn't specific to the course, but it's sort of like human labeled, and that actually works really well. We found that we can actually generalize quite effectively. The other way to do this is called domain adaptation. We have an archive paper on this, where basically you take the existing model from another course and you adapt it to a new course online. So while you get data from the course, you're actually updating a model that's trained on that data, even without any labels, which is very interesting. And that also works pretty well. So in conclusion, first, the interesting thing is logistic regression is pretty accurate at predicting who will graduate. In just 3 weeks, you can accurately predict. And deep learning can do even better, and you don't need to do too much like hand-coded feature engineering for this. We've actually used this to help students graduate by essentially focusing our efforts. So we sort of focus the messages we send to students, and we only send them to people who are sort of borderline. And then we found that this actually improved people's graduation rates and interaction with the website. We also found that it's important that these messages be personalized, and so this gives us a way to do that. We also have mentors focus on who they're going to talk to based on who is kind of on the edge. So like, if someone is like very likely to graduate by themselves, you don't need to do anything. You just let them go. But if someone's very unlikely to graduate, you also, you can try, but you might not have a very strong effect. And so what you can do is just focus on the middle range, like people who are, according to your models, either they've suddenly changed, like, they were doing really well for 3 weeks, and then all of a sudden after the 4th week, they're not doing as well. You can focus on them as well. So that's it. Do you guys have any questions?
Could you say a little bit more about that borderline intervention? What was sort of the scoring variable that made you decide to send the message or not?
Right. So this model is calibrated in the sense that it tries to predict the absolute probability of graduation. So when it outputs a number, it's not just sorted, it's actually, like, if it says 85%, we actually did the test and validated that. If it says 85%, it is actually 85%. If we took all people in that bucket, there's an 85% chance that they will graduate. The reason I'm mentioning this is you can kind of decide, like, I'm going to focus on people who have only a 70% chance of graduation, right? And so you can decide for yourself, like, what is that threshold for you? We chose, I think it was like, we tried a couple of different numbers, but I think we did about 70% was the one we focused on, like between 70 and 75. But since these numbers are calibrated, you can kind of decide, like, intuitively, like, when do you want to focus on talking to someone.
So it sounds like, are you familiar with a technique called regression discontinuity?
No.
Oh, let's talk offline.
Okay, cool.
What are the embeddings?
In the deep learning model. So for every event, essentially take the cross product of the event ID and the number of days since the start of the course for that student. So essentially it's like, if you imagine a matrix, a sparse matrix where events are rows and columns are days since the start of the course, and there's like a 1. Like if a student did this event 5 days in, 6 days in, 7 days in.
That's very sparse.
Yeah, and then you just vec it, essentially. Like turn it into a vector, and that's like the input to the
That's a sparse vector.
Yes, very sparse.
So, but embedding vectors are usually dense vectors, like word embeddings, right? So that's why you have.
Oh, we're not using any embedding.
Oh, so it's not actually an embedding, it's just a vector representation.
Yes.
Back of what's vector representation.
Yeah.
I see. Okay.
Hop, do you want to
Yeah,
answer
actually
me?
you go through we don't use any kind of pre-trained embedding, but we go through the embedding layer. So basically mapping this first one vector to the dense representation, like a smaller vector. So that's what we did with the first layer.
It's like learning an embedding.
I mean, you do some script training like word embed.
So
Yeah, let me bring the slide up. It's
yeah. Yeah. So basically, kind of rather than kind of having, so there are 2 approaches. So kind of train the kind of embedding in a separate way, or you kind of put kind of the embedding into so the kind of very bottom is the input, and then the second layer is the embedding layer.
Right.
So embedding layer is kind of everything is put into a single network. That'll be much easier. So basically, the input is sparse representation, and then the output of that green embedding layer is dense network. That's the dense network, just a fully connected network.
Oh, so there's a fully connected, just past this fully connected,
Yeah.
output of fully
Yeah,
connected.
but
Okay.
but that kind of dimension is much smaller than the input dimension.
Sure, I understand how it is. It's basically it's a keras tag.
Yeah, whatever state is different.
Sure.
Yeah.
I missed the first minute, I don't know if you covered this. So it looks like it's semi-accuracy unit, like at the very, very beginning. So there's some information before, like they even have behavior on this class.
1 week is, it means after 1 week of data.
Oh, okay.
So it's the first week.
Do you use the course
Information?
or student attributes?
With this data, no. Yeah.
Okay.
We've
So
done other-
kind of, yeah, week 1 is kind of the 1 week after registration,
Okay.
or kind of full start.
Though we've done other experiments where we have features of the student, like where we ask them a bunch of assessment questions before they took the course,
Yeah.
and that does actually help it a lot. I was just trying to think whether this data had that, and it doesn't. This one is not showing that model.
How much data do you think is necessary to make the neural network well? Sorry, that's just for your talk. How much data is necessary to make this work well, and why isn't this turning out?
So I think we have here 8,300 students, and the first one was like 1,800 students. So I know the logistic regression one doesn't require that much data, but even the deep learning one doesn't require that much data. A couple of thousand students.
And given that I think others have tried this sort of thing with MOOC data, so why does it work well for you and maybe didn't for others?
I think that is the model issue. Yeah, neural network model was not good enough. So basically, kind of, can you
Well,
express? Yeah. So there are two reasons. This is state of art for the student performance prediction for now. So there is kind of two drawbacks of the past approaches. One is like kind of people, rather than just trying to feed the model with just a raw input, they try to come up with the feature engineering first. So feature engineering basically can reduce the dimension of the input somewhat. So that kind of limit the potential use of the physical gain we could have from the neural net. So that is one. And then two is like model was not so just kind of I think when you look at it, it's kind of global max pooling. If you're familiar with like some level of like attention layer, this layer kind of is like a hard attention layer. This is kind of crucial. So basically, you can look at the kind of the student activity as a sequence perspective. So starting from day 0 and day kind of like day 60, that's a long sequence. You need to kind of find out some span you need to kind of focus your attention, right? So if you look at everything, it's hard to make some good decision, but like, that's another.
But it is true the logistic regression model also works.
Yeah.
Yeah, your logistic regression
Yeah.
model also worked.
Yeah, but so far, like, so like people have attempted a lot of, but it was hard to beat the logistic regression. The first thing that kind of make us kind of beat the logistic regression with a certain good margin.
But a small amount. So I'm kind of wondering why did the logistic regression work well when maybe in other new studies it hasn't necessarily?
We haven't tried it on other people. We don't have access, or we couldn't get access to someone else's data, so we don't know why it doesn't work for them. I suspect though that it would partially it's that our baseline graduation rate is just higher than other MOOCs, right? And so if you have a baseline, it's very hard to do, like if your baseline is like 1%, it's kind of hard to do a lot better than that. But if the baseline is already like 12 or 50%, I mean, that makes the problem a lot more
That's
balanced.
probably the right answer is that people are paying or they're more staying more. It's not just random people are joining.
Yeah, and then the balance problem in general is like, it means the value of your data is also higher, right? Because like each example, if it's a very imbalanced data set, the value of an additional sample is very low, right? So I think that might be why.
Right. How effective are your interventions? Okay. Like have you run A/B tests on that?
Great question. I don't have the data here. However, we found that it was, I'm trying to remember the exact numbers. It was significantly, we were able to sort of increase the amount of time the student would come to class by like 2 times. So like we would take some students whose average time of coming to class was like 1 point something, and we increased that to 2 point something. I don't remember the exact numbers, but it was like on that order of improvement. But that was That was not just due to this, that was also due to messaging. So we send out text messages to students that are personalized based on what they've actually done in the class. So that's sort of an application of this technology, but it's not like, I couldn't say it's like just directly due to this, obviously.
Okay, I think we're out of time, so let's thank the speakers.